Hello guys, I welcome you to the channel Notability Tech on Tube. Yet again, offering you some of the free exercises on numericals just to enhance our capabilities and understanding towards aerodynamics. And I've taken an example from the book Fundamentals of Aerodynamics, which is third edition, John D. Anderson Jr., University of Maryland, and it's been actually in the semester course IIT Kanpur. And I'm going to actually read out first of all the example, and I'm going to solve it out later on. And it's of two parts, and I'm going to actually solve the equation which is the basis of this numerical or problem, and afterwards it may be consist of two parts. The whole video is just to solve the first the numerical, and later on we're going to solve out this equation, which is a Newtonian sine squared law. So first of all, reading out the example, consider a cone at 0 angle in a hypersonic flow, which is normally the speed of sound in the environment as compared to the speed of the body, which is normally is the aircraft. The half angle, which is the half deflection angle of the cone, is theta c as shown. This is the spherical part or the spherical side, and this is the sideways picture or pictorial representation showing the cone. And also it is normally flowing in a shock wave in an environment, in the sounding environment, with the angle which is theta c, which is the half deflection angle, and with the r, and which is the radius, and it's been shown over here as well. And we're going to take it rb, and we're going to take it as a full rb radius, or the base of the radius. It will be like that. And p infinity is the free stream pressure. Okay, and normally x on the back side, that is why it has been shown as p of infinity, and x is the difference, is the distance between x is normally the distance between the cone edge towards the r, and this is normally x, and dx is the difference because we're going to apply the pressure over here, and it's just taking the sum part of that cone, and the difference between x and dx is mentioned like that. That is the difference between dx. And when you're going to take the derivative, we normally have to consider that the sign normally applies when it is the perpendicular form. So it would be in the, that is why our radius is in the perpendicular side, so it would be sine theta will obviously be there. So we're taking dr, the derivative of radius, into sine theta, which is the whole part difference of this, which is the area as far as this part is concerned, taken in the example. And this c is the coefficient normally, and it is given as this, and it is the circumference as well normally. And we're going to see how we're going to solve it out and approximate expression for the pressure coefficient on the surface of a hypersonic body is given by the Newtonian sine squared law, which is cp2 sine square of theta c, okay, which is the half deflection angle of the cone. This is whole the cone. It is all about the cone, and it is the angle of the cone, the deflection angle of the cone, which is represented by 2 sine squared theta c. And we're going to prove later on in our video how we're going to solve this actually Newtonian sine squared law. Note that cp, hence p, which is the pressure, is constant along the inclined surface of the cone, and which is the inclined surface is this one. Along the base of the body, we assume that P is equal to pressure at the back side, which is pressure infinity, and normally we take the pressure X as a difference while getting applied as a force. Okay, so that is why it is normally shown as this. Neglecting the effect of friction, obtain an expression for the drag coefficient of the cone, where CD, okay, which is the drag coefficient, is based on the area of the base. So let's see how we're going to solve it out. Normally we have to find first of all the coefficient CD of drag. That is our requirement. And first of all, Newton proposed that force on any object offered by fluid flowing is directly proportional to sine square of theta, which is the flow deflection. That you need to know as by the Newton proposal. And when we're going to take it out, let's see how we're going to solve it out. And it is the flow deflection in terms of the angle which normally is created from that cone, and obviously it is at the front side, so that is why it is the flow deflection of the fluid. So the drag force which is normally, this is the drag force which is normally applied as a difference of P and P infinity, and shaded strip of surface area, it is normally on the shaded strip of surface area. We're going to take it as P sine of angle of deflection, and then it is 2 pi of r, which is normally the circumference, and it is the difference of dr into sine of this, which is normally the part of that, is normally it is this part. This is the area of that part we've taken along with the circumference, and we applied it with P sine theta c. We are applying it as a drag force. Okay, so that is why it obviously, when we TPR, and it would be P of dr, we have to take the difference of this and this. Okay, when pressure applied on the area, which is normally represented by this, and we have to actually represent this whole drag force which is on this shaded area. So the strip area of a surface, then we're going to represent it like this. And when we're going to solve it out, so normally it is in the derivative form. When we're going to take out the derivative, we have to take the integration. And taking out the integration, let's see if it's d is equal to 0 of rb into 2 pi r, which is rb is the radius of the base, p dr, minus 0 of rb 2 pi. Now I have to take that p infinity into dr. So that is how it has been applied. 2 pi, which is 2 pi r. I've taken this. Okay, first of all I have applied the drag force on this, and minus 0 to in rb 2 pi p infinity into dr. And when I'm going to apply the drag force, that would be 0 to rb, just adding both of them, 2 pi rp minus p of infinity into dr. And when we're going to apply pi into p into this to rb of square, so that would be the whole. We have to apply the drag force as a difference of the pressure. That is why I've taken it the difference in terms of drag force. Okay, so obviously it has been in the difference of the pressure, so we have to take it like this. But just to remove the infinite or the derivative part, we have to take the integral from 0 to rb, that is the whole area of that radius, or the whole surface area of the cone, and that is represented by the radius of RB, and also been shown in the picture as well. And when I'm going to, I have actually removed the integral, and it's been shown like this. So it would be pi P into P naught RB square. Okay, just adding this over here, it will be RB square over 2. So 2 has been cancelled, so that is why it is now being represented at this. So reference to the base area pi RB square, which is this and this. Okay, the drag coefficient, and I believe the drag and the drag force, the drag coefficient, and because that is also the requirement of our problem, you have to find the drag coefficient, and reference to the base area, which is pi RB square. The drag coefficient is, now this is the drag coefficient CD, and that would be drag force divided by Q of infinity into pi RB square. Okay, so that would be, drag force would be pi RB square P or P of infinity divided by pi RB square into Q of infinity. So that would be this, and the whole force would be equal to CP, and CD is equal to this. So C of D is equal to 2 sine square theta C. So obviously that coefficient, the drag coefficient, is now equal to the pressure coefficient. Okay, and pressure coefficient is represented by 2 sine square, which is Newtonian sine square law. So the drag coefficient is also 2 sine squared, or the Newtonian sine square law. So that is our requirement. So what we have actually find it out, CD. Okay, so this part is normally this, you need to remember that CD is equal to drag of Q not pi RB square, and Q over here is being normally like this, so you can easily see that how it's been taken, and we're going to apply it, and that will help us to get the coefficient of pressure, and which is equal to the coefficient, drag coefficient. So the second part, in my opinion, is just to prove this. Prove CD is equal to CP, for example, in this case 2 sine square of theta, which is the Newtonian sine square law, and also it is referred to as the approximation in hypersonic inviscid flows, and also it is referred as local surface inclination techniques, and what we have taken is Newtonian technique. Okay, so we're going to prove, we have ended over there. Now we're going to prove this. There are normally the modified Newtonian technique as well, but right now we're just going to cover the local surface inclination technique, which is the Newtonian technique, obviously represented by the Newtonian sine squared law. So we're going to prove it, which is under the umbrella of under the umbrella of approximation in hypersonic and viscid flows, covering various topics, and this local surface inclination technique is one of the topic under this umbrella. So we're going to cover this. Let's see how we're going to apply. And for example, this is the inclined surface. The velocity is v naught, and this is applied over here, and we're going to take it as such. This is theta, a sine of theta, like this. So velocity normal to surface is v of naught sine theta, which is normally represented by this. V naught is of sine of theta because it has been applied vertically. Mass flux blocked by surface, that would be rho infinity, that one would be sine of theta. And momentum lost by fluid per minute. Okay, this is the mass which is represented in the terms of rho into velocity, and the gain would be into this a sine of theta into v naught it is v naught sine of theta, and multiplying it velocity square into a sine square of theta. So momentum now is being converted over to force applied by fluid. So the force is now equal to rho of infinity and this square into a sine square of theta. And this is whole momentum is now been converted into force. Force divided by a is equal to rho infinity velocity infinity square sine square of theta. And that would be whole represented in terms of the difference of the free. Normally we're going to represent the force applied in terms of the difference, which is p into p naught or p infinity, and that would be p infinity velocity infinity square sine square of theta. So normally, as I said earlier, when I'm solving this Newtonian sine squared law as a numerical, I've told that pressure acts as a difference while applied as a force. That is why I've taken this as a difference. So when we're going to solve it out with the help of the example, and also we're going to help it out, solve it out with the help of this momentum and also the force relationship, will help to actually get the Newtonian sine squared law. And in this example, obviously we'll just dividing and multiplying and dividing by 2. That would be rho into this divided by 2 and multiplying by 2, and that would be over here p v naught square into sine square theta, and p into infinity 2 rho of infinity v naught square into 2 sine square theta. So that would be the half. Okay, so this whole, as we have discussed earlier, this is normally the coefficient for pressure. So this whole value would normally be equal to the Cp and is equal to 2 sine square of theta, where theta is the flow deflection angle. Flow deflection angle. So that is the whole value. So this is Cp is equal to 2 sine square of theta, and I have actually this example which we have applied. Why we have taken it to the equal to the coefficient of pressure? Because we have learned that this whole stuff is also equal to the coefficient of pressure when we taken it as an base area, which is pi rp square. And in this example, it is the relationship between force and momentum. Okay, and that is why the pressure in terms of force and momentum is represented, and also this is equal to the coefficient of pressure. So this is 2 sine square of theta, which is theta is equal to flow deflection angle. So I hope that I have, what you can say, help you understand a bit of a numerical about Newtonian sine square law, and also explain with the help of cone, hypersonic flow, and also the full numerical has been explained. So this is all about this numerical. So I have explained with the help of first of all the proposal of Newton proposal, which is force is equal to directly proportional of sine square of theta, which is the flow deflection. We're going to cover with the help of the pressure, we're going to cover with the help of the radius, and the momentum, the difference between the area, the difference between the pressure, and we're going to represent it by P minus P of infinity, and that is why we have taken the area of the cone, a specific area, when going to apply the pressure over here, and taken the vertical or the vertical radius RB, just applying the derivative, because derivative of the difference dx is represented by this cone area, and we're going to apply the force. This cone area has been represented by the is applied on the pressure is applied on this, and we have taken the hypersonic flow, which is normally the comparison of the flow or the speed of sound as compared to the speed of the body. So, and it is represented by Mach 1 to Mach 2, Mach 3, Mach 4. It is normally for hypersonic and supersonic bodies like aircraft, it is Mach 5 and above. So obviously it is that relationship we're going to discuss as far as the hypersonic flow is concerned. We're going to have discussed in terms of cone. We we have applied the deflection angle, and we have discussed how we're going to apply our deflection angle and use the deflection angle to get the coefficient of pressure and the coefficient of drag, and it is represented by 2 sine square of theta. Why it has been represented by 2 sine square theta? We have actually solved that problem as well and solved that proof or theorem. So you can also visit for the inclination services or the inclined local service inclination technique. So for that we have discussed the Newton technique, and we have applied this one. So I hope that we have covered the coefficient of drag, which is normally it is equal to this, the Newtonian sine square law, and we have covered with the help of the derivatives taken as a part of that sphere, and we applied it just to remove it. I applied it the integral from 0 to RB, getting it in the terms of difference, just converting it into the parts, which is coefficient of frict pressure, it will be equal to this drag, and we have got that the coefficient of drag as well. So I've applied the example as well. So I hope to see you in the next some video which is more informative, more knowledge as far as the fundamentals of aerodynamics is concerned. Let's see you in the next video. Hope to see you soon. Thank you very much. Take care and have a nice day.